Hey everyone, hello. Welcome to this exciting session on boosting numeric computations in Python with a C++ integration. My name is Mandar Deshpande. I'm a software engineer at PyTorch, where I optimize performance of recommendation systems. So today we're going to dive into a topic which is at the core of modern machine learning, how to enhance the speed and efficiency of numeric computations in Python. So Python is incredibly popular for its simplicity and ease of use, and it supports a wide array of libraries across web development, app development. You build like backend systems and DBs in Python. But Python can sometimes fall short when it comes to performance. By leveraging C++, which powers the underlying performance of libraries like numpy, scipy, and even deep learning libraries like TensorFlow and PyTorch, we can also boost our own applications. So in this talk, we'll explore how such integrations can be done for our own app, and we can boost the performance, enhancing efficiency across various computing platforms, whether CPUs, GPUs, or this Apple Silicon. So let's dive right into it. So performance is really crucial for any kind of numeric computation stack, whether it's numpy, scipy, or your deep learning libraries. You would ask why. Mainly, all these modern software systems handles massive data sets where efficient computations can significantly reduce your processing time and resource usage. Moreover, moving to complex calculations we perform ranging from all this linear algebra, matrix manipulations we do, or all the statistical computations we do, all of these would benefit if we have optimized performance so that the results can be generated swiftly and accurately. Now let's also consider, I'm not changing the slides. Okay. Let's also consider real-time processing in applications like real-time data analysis, quants, or even machine learning inference at endpoints. All of this requires that you have really efficient and performant numeric stacks. Furthermore, as we grow our resource efficiency across CPUs or GPUs, there's an effect to the bottom line, like how many CPUs or how much is your memory utilization for your application would affect how much money you are putting into serving up your app. Furthermore, as we scale our projects to bigger sizes or more users or across countries, the performance of the libraries matter even more. So overall, it affects your user experience, and at the high level, it affects the trust the customer has in the end product you're going to offer with these computations. Plus also giving you bottom line improvements in the money you're going to make on the application. So let's start by understanding the foundational nature of Python. Why is it really slow? Primarily, it's an interpreted language, as we all know. We don't compile it, it's interpreted line by line. So it has some additional overhead. Plus, we have this global interpreter lock, which is well-known constraint within the Python ecosystem. So it only allows for one thread to execute at a time in a single Python process. So what does this mean for us? It's a really problematic issue when it comes to leveraging multi-core processors, which are common nowadays with GPUs and all these custom silicon coming up. Then there's this issue with dynamic typing, where all the types of your variables are going to be defined at the runtime. You can't define it upfront, so Python is going to add an additional layer of processing overhead for type checking and validations. There are other issues around memory consumption because how Python manages its own memory. You can't do low-level memory management because of the high-level data structures we use in the model. And finally, since again it's not a compiled language, there are limited optimizations available for us to use. There's no inlining, no loop unrolling, or all such things. So all these techniques, which should ideally speed up your compute-intensive tasks, they are not natively available in Python, which leads to some slowdown in our performance. So how do all these numeric computation libraries actually work around these issues? So that's the primary goal of this talk. They usually abstract out all this compute-intensive task in C or C++ code, and then they build like wrappers around this, which can be called through, say, PyBind or Swig or Cythons or something which is going to use that low-level language, help us get around the GIL, and give us the performance boost we need. Then there are other optimized libraries like Intel's MKL, the math kernel library, or OpenBLAS, which are built on some other low-level language like Fortran or other languages. We could also use parallel computing, including multi-threading. We are going to work around the GIL and leave the lock on the GIL where you want to perform any heavy computations. Or use multiprocessing using libraries in C++ like OpenMP. And this is the hot topic, GPU acceleration, where you are using more and more GPUs in your workflows. Since most of these machine learning models or deep learning models can be designed as a DAG, like a directed acyclic graph, you can compile them upfront and then run them on your GPUs. So libraries like TensorFlow or PyTorch already offer such optimizations natively in all these ops they offer. So there are some other ways to do it, like you can do just-in-time compilation or batch processing. But what's our overall focus here? We want to focus on things which will mostly not change in the future. And that's using some low-level language to wrap Python code and use it such that you can boost your performance. So overall, what options do we have for our simple applications? We are not trying to do anything really complicated right now. We are not running any deep learning models. What about the simple applications? You could do something like Python. Now, Python is primarily designed to extend Python with C and C++ code, but it is more Python-centric and less focused on seamless C++ integration. So if you have any optimized code already written in C++, you can't actually use it in Python because the generated code is a bit more cumbersome to manage. The pyx file which you generate has all this C defs and type defs defined, which make it an issue. So we'll not focus on Python for now. C types also has limited support, since it's only designed for C, and integrating it with C++ would mean you are having some workarounds, and you can make it work, but there's a lot of features missing, like overloading or classes, which are not available through C types. So overall, what we are focusing here is you want to write your code in Python, but only for the compute-intensive part. The low-level language which you choose should also be powerful. So C++ is one such language which offers all these inheritance, overloading, objects, and all the constructs which you are already available in Python, but in a performant package. So we'll just focus on PyBind, since it's giving us all the features of C++, all the modern C++ features, where you can have classes, inheritance, exceptions, and smart pointers without doing any cumbersome integration. You just build your own C++ code. It's really easy to use. It's a header-only library. It offers a seamless integration with Python. And you can naturally use C++ and Python, mix them up as per your need. Also, the bindings generated by PyBind 11 are really efficient, as in they are as efficient as handwritten code. So there is minimal overhead for you for any performance critical components. And one of the main key benefits is zero copy data exchanges. So when we talk about machine learning or deep learning workflows, there's a lot of I/O going on between your host and your own device. So example, you want to run something on your GPU, let's say just matrix multiplication. So every call you make on the GPU, you have to pass your data from your local storage to the HBM on your GPU and pass it again back and forth as many operations you do. But with PyBind, you don't have to do any such copies, since it offers the zero copy data exchanges between Python and the C++ layers. Plus, it supports multiple compilers across CPUs, GPUs, whether this can be your Clang, LLVM, GCC, or your NVIDIA PGI compilers. So overall, you are a developer, you're already facing a ton of stress, trying to optimize your workloads, trying to improve your bottom lines. So all you care about is your peace of mind. And CBind, like PyBind 11 is giving us exactly the same. So let's just work through a really simple demo. This is just a demonstration, it's not going to be a real use case. But if we take any modern deep learning problem, the basic problem we are solving is of matrix multiplication. So let's just take a vanilla implementation between Python and C++, both of which are using just simple for loops, and see what kind of numbers we get in terms of performance. Say is a simple Python code. You are just running 2 for loops over your n by n matrix, generating your resultant matrix in a third loop, and then returning your result. Similarly, I'm doing the same in C++. If you see, there's no difference in code as such. It's just a syntax difference between Python and C++. The only difference is we are building this new pybind module where we are defining what kind of binary we want to build. That's the mat-mul CPP binary, and what function we are defining inside it. So this mdef matrix multiply is the actual function we are going to call from our Python code to compare the performance. Okay. Now this is the setup file which we can use to build the actual compiled binary or the .so file for your C++ code. It's very simple. It's just a setup file. You mention your C++ binary name, what modules you want to extract, and your command to build it. Let's just build a binary. You get this SO file, and now we have this simple script to compare you're not doing anything special here. We're just comparing the time it takes to run matrix multiplication for a n by n matrix, where n is 100 to start with, and we can check how it does for n is equal to 1000. So you can see, comparing Python and C++, when n is 100, you get almost a 79x improvement when you use pybind for the same code without any improvements in the algorithm itself. Just using pybind and using your C++ code in Python, you get a 79x improvement. When you scale it up to 1000, you get like almost a 57x, and such trend is followed when you keep increasing n. So there are much more optimizations to be done here, but this is just a simple demonstration of what all is possible and what all pybind offers. Let me just have a drink of water. So overall, the integration of C++ with Python is not just theoretical, but a proven strategy that has been used across the industry. And this has propelled the capabilities of several high-profile libraries. You might have already used numpy, scipy, or pandas, which are all built on top of wrapping the heavy computations through C++ and then using them in Python. Or you might have enabled faster processing for SQL engines like MongoDB or MySQL. All of these do the query generation and extraction or the resolution through C++ code, though our interface through it is through Python. Then there are other deep learning libraries which are very common, like I already mentioned, PyTorch and TensorFlow. All of them are building all these complex graph of operations, which are like a directed acyclic graphs. And all the optimizations on top of these graphs, graph rewriting or deduplicating of the graph nodes or removing any common sub-expressions, all of this happens in the C++ layer, just that the developer's experience needs to be simple, so it's interfaced through Python. So you can see this approach has been widely adopted in the industry, leading to significant improvements in scalability and efficiency across various applications. So overall, you have got this bunch of libraries, OpenCV, even the Blender tool, which we use for 3D modeling, is built as a C++ backend, and then you have like Python to do all the interfacing with it. So such use cases are going to be really common. What we want to focus on is the big picture. So what's the big picture? Right now, there are only a handful of companies. And when we say handful, there are still like 15, 20 companies which are handcrafting all these custom silicons or custom hardware stacks. And they are co-designing the AI software hardware stack for their own use cases. They are fine-tuning it for their own requirements based on what they want to do. Example, Instagram wants to do video processing, so they would build a chip just to do video encoding and decoding. Say Amazon wants to serve better search results on their e-commerce websites. They would optimize their Trainium and Inferentia chips just for that. Google is now on their 6th iteration of the TPU, like the tensor processing unit, which just came out 2 months ago. And they are trying to optimize it just for their training and inference workloads. So these are just a bunch of companies doing this right now. But what we want to focus on is the longer trend. And the longer trends are that more and more people are going to build their own custom silicon, and writing such custom code for compute intensive load is going to become a commodity. You won't need to be part of big companies to actually optimize your code, because compute is going to become really cheap. So looking ahead at the future of programming and systems development, there are several key trends and technologies which demand our attention. So primarily the area where I am also focused on is systems programming. So the overall field of systems programming is evolving. It's pushing us towards more efficient and robust infrastructure. You might have seen the Llama 3.1 model training stack. It was trained on close to 16K GPUs over a duration of 74 days, and it only had some 4 faults, like 4 minor checkpointing faults. So all of these things mean that you are actually doing a great job at systems programming. And that means that we need to improve our loop of optimizing, profiling, optimizing such loops for writing all these kernels, whether it's for GPUs or you're writing custom kernels for, say, Intel CPUs, or it can be any custom hardware. Furthermore, there's a Python enhancement proposal which got accepted last year, this PEP 703 for no-GIL Python, which has already, I think it's already launched in Python 3.13. So maybe it's going to be a partial rollout. They are still testing it out. But it's going to change how we approach the paradigm of programming numeric computations. We don't need to actually rely just on, say, multi-threading or multiprocessing or just C++. We have to look at the entire package. There are multiple tools in our toolbox, and we need to see which of them serve our purpose the best. So this, you might have also read about Mojo, which is being developed by Chris Latner. So they are saying that the interface would stay the same. You would still use the same Python language. But under that, they're building all this custom accelerated engine called Max for serving machine learning and deep learning models. So they are approaching it from a different angle. Then there's companies like OpenAI, AMD, and Meta, which are partners. Happy to take any questions.
The zero beta copy.
Yeah.
Is there some detail under the hood how it works?
So it's just referencing pointers. So PyBind also allows smart pointers to be accessed through Python. So you don't actually have to send a copy of the data. You can just send a reference to the data.
Okay.
Yeah. Yeah.
Because in one of your slides, you talk about other tools to use C++ through Python. You mentioned 2 of them. Why didn't you, like for Swig and Python C API, what were the concerns of why not using those?
So Swig, like the simplified wrapper interface, it generates all these wrappers, but then there's a lot of boilerplate code also which gets generated along with it. So you have to use all of it, and it becomes cumbersome as your C++ code grows. It's okay for standalone units, but say you're writing a query rewriting engine, or you're writing a data infra layer where you want to take out queries, fetch all the Hive data, do some data conversion. Now as your stack grows, Swig becomes a bit more cumbersome to handle. And what was the other part, like the Python C API?
Yeah.
So again, Python C API also has these custom Python objects which you need to manage. It's not very, how do I say, it's not very Pythonic, and it's not very C++-like as well. So it's somewhere in between. So you either want this clear delineation where you have someone on your team who is really an expert in C++ or someone on the Python side, or you are going to mix it, you can create some workarounds for it and use like the Python C API. I think it can work. Like we have tried it out, but the way it works for complex use cases, it doesn't support. I think it doesn't support inheritance and some like complex C++ constructs. Yeah. Yeah.
So I think it's on the next slide. Yeah, this one. Can you explain the zero copy data exchange here?
Yeah, just a minute. So yeah, so mainly the smart pointers, like where you have a data already referenced, say you have a tensor in the C++ layer, you're doing some manipulations on top of it. You don't need to pass all of the data from the C++ layer to Python for it to be processed. You can just pass a pointer to the data, and that's still okay with PyBind, which is not usually doable in all other wrappers.
So then in that case, the application will reference the data on the disk
Yes,
without the loop.
correct, yeah. It doesn't need to like copy over the data to a new memory address. It's going to reference the same memory address.
Even if that data is on the GPU.
So when it's on the GPU, your Python code, like the code which you call on top of that, should also be GPU native, because anything you do on the GPU would be on the GPU's memory. And if you're going to do any I/O on the CPU side, you'll need to again do that hopping. So I can share more on like why we do all of this and why is this important. So mainly I mentioned like I optimize recommendation systems. So there are a bunch of use cases at Meta where we do like serving time optimizations for ads or feeds, reel or IG, all of these use cases. So they are already working quite well. Everything is going well. But if you can boost the QPS or latency, how much CPU time or GPU time each of this inference is going to take, there's going to be a huge gain in when you scale it to like billions of requests per day, there's like a huge gain in terms of money as well, plus what experience the user gets. So what we usually do is we perform like strobe light profiling on our code, look at the bottlenecks, see where we are doing some copies or not, and then abstract out that part of the code, whether it's in Python. If it's in Python, we'll abstract it out to say PyTorch torch binded some native C++ code, or if it's already on Python side and it's doing native PyTorch code, we'll see if we can run it on GPUs. So all this graph rewriting or optimizations are very, how do I say, they're very ad hoc, and they require us to profile it and understand like where are the bottlenecks.
In your experiment, you saw it 10x gain, right? Between C++ and.
Oh, it's almost a 79x gain
Okay.
for n is equal to 100, and for 1000 it's 57x. Also it grows, like the thing over here is we are just doing simple for loops here, but there are a bunch of cases when you're building say neural networks that you write all your code in Python, it's using say TensorFlow or PyTorch, and then you serialize your code in some format like torch script or torch trace code, and then it's served in some C++ runtime. Now torch script or torch trace, all of these things are not shape aware. So you need to find a way to write your code that during runtime, those shapes can be inferred without any fixed shapes being known upfront. So example, you're writing a Python code, your input matrix is say 50 into 25. It's usually not the case, it's usually in the power of 2s. But say your shapes are already fixed. But when you run it on the GPU, these shapes cannot be inferred at runtime. They should be known beforehand. So because of that, all this Python code is usually abstracted in C++, so that these shapes can also be inferred during runtime. Because Python is not compiled as such. The serialized code is compiled as torch script or torch trace, or TensorFlow will use something called, what do they call it? They have a backend for TensorFlow where they serialize the code, and then it's deserialized in the Python like C++ runtime. So there are like many such scenarios where you can't use Python when it's compute intensive or resource intensive. Okay, I think that's all. Yeah, thank you.